Hi, everyone. Looks like we're back at this again. Um, just wanted to fill you in on a few things that has happened here in this last week and a half with regards to our class. But last we left off, you were learning parametric polar vector topics. If you have not heard, I haven't written this out yet in Skyward. I don't know if I will yet or not, just because everything's not completely official yet. But it does seem as if you're going to be able to take the AP test. It's going to be an online AP test. It's going to be a 45-minute all-free response. And the topics of parametric polar and vectors that we just wrapped up, or we're planning to wrap up, is not going to be on there. So as a result, since our time is somewhat limited, and I don't know if I'll ever see you again, and I said that the last few days of class joking, now I'm legitimately concerned about that. So we'll find out soon enough how that's gonna play out. But it turns out that those topics, parametric, polar, and vectors, are ultimately not going to be on the AP test, the abbreviated AP test that you're going to take. However, there are about half the topics in our next chapter, our final chapter, that are going to be on the AP test. So as a result, we're going to move along. We're not going to spend any time in terms of an online test on that topic that we had dealt with before. You've seen it, you know it pretty well. If you were to see it again in the future, I think you'll be able to handle it and do just fine. But we're going to move on. We're going to go ahead and start with this next chapter. The next 5 weeks of class will be basically comprised of doing this and then reviewing the topics that are going to be on the AP test. So it does help us a little bit since we're a little bit ahead of where everybody else would have been, it would seem, around the country, that we can really focus on the topics that will be on the AP test from this next chapter. And then on the other days, we can go through the reviews and do whatever we can, either face-to-face or online. So with that being said, we'll go ahead and get started on today's notes. Pretty simple. You'll get 2 copies. It's really 2 sections, 8.2, 8.3. We'll go through those. Both of them are pretty simple. If you look at the top here, 8.2 is what we're going to start with. It's called indeterminate form, Hopital's rule. First thing we want to identify is, what does this actually mean, indeterminate form? Indeterminate form is typically 0 over 0, but it also is infinity over infinity, because we just can't determine really what's going to be going on. Typically, anything, when you do 0 by any number, you're going to get a 0. So we have that when it's a 0 over a 0. But in the same way, if you have any number divided by 0, that pretty much is always going to make this undefined. And any number that gets divided by itself, so 2 divided by 2, should be a 1, which we also have here. So we have a 0 on top, we have a 0 on the bottom, we have one number getting divided by itself. So we have a lot of conflicts in terms of general rules of math and how they or what that should result in. So because of that, it's called indeterminate. Same with infinity over infinity, in the sense that if it's infinity over infinity, what does that actually mean? Because this really could be 0, it could be 1, it could really be anything. But that's indeterminate. If we get 0 over 0 or infinity over infinity. If something is of indeterminate form, so again, one of these 2 things are the ones that we're going to be dealing with, then we can use what's called, if I can stretch this out just a little bit, or just bring it down, Hopital's rule. All right, using Hopital's rule, what that allows us to do is use derivatives to find our limit. So if you look at this first problem that I gave you here, if we went ahead with our rules of limits and we just substitute in, like we normally would do, let x be a 0 here, let x be a 0 here, we obviously get a 0 on top, and then the tangent of 0 is also 0. So because of that, we get 0 over 0. That is obviously what we would call our indeterminate form. Okay. Now, we know the answer to this question. This is something that we did. I don't know why that thing is there all the time. What is that all about? It's going to be very annoying. Erase that. There we go. We know this answer should be 1. It's our old little shortcut when we have sine on top or bottom, or if it's a tangent on top or bottom and we're approaching a 0, or we could just look at our coefficients and get this little 1 over a 1. And we know that limit should be a 1. So if you threw that into your calculator and graphed it, you're going to see that this is a 1. So L'Hopital's rule should give us that same value, but it's a little different way. It's a nice little shortcut. It's a nice little trick that allows us to deal with some of our limits that we dealt with earlier in the year. We didn't know derivatives at that time, so we couldn't have used it. But what L'Hopital's rule tells us, if we kind of really focus in on here, I'll try to save you some time so you're not bored out of your minds. If I want to find the limit as, it doesn't have to be 0. A lot of times it'll be 0, but as x approaches some number, if I go ahead and take this 0 and I go ahead and throw this in and I get what we call indeterminate, which is a 0 on top and a 0 on the bottom, then if it's of indeterminate form, we can actually use their derivatives. So notice how these are the derivatives of each of these, and go ahead and take the derivative of each, find that limit again as x approaches, in this case, a 0. Whatever that gives us is our answer. If that does not work, as long as we once again were to get a 0 over 0, then we could actually move along to our second derivatives. That would give us our answer as long as it's not indeterminate. Okay, so if we look at this first problem here, see if we can kind of understand what this is saying. We know this answer should be 1. We talked about that earlier, and at the beginning of the year we dealt with that. If we use L'Hopital's rule, knowing that if I plug in a 0 on top, I get a 0. The tangent of 0 would give me a 0. I get my indeterminate form. What we're going to do is L'Hopital's rule says, let's take their derivatives. So if I take the derivative of x, that's going to give me this 1 here. If I take the derivative of tangent, that's going to give me secant squared of x, and I'm now going to evaluate that at 0. So the 1 in the numerator obviously is going to remain a 1. If we go ahead and let this x be a 0 here, just right over the top, the secant of 0 is a 1. If we want secant squared of 1, it's going to be a 1. So this produces 1, and we get what we knew we should get, which is a 1 for our limit. So it's just really using our derivatives. The thing to be careful of is we don't do the quotient rule when we're taking our derivative. So it's a fraction, but L'Hopital's rule is just the derivative of the top, derivative of the bottom. We divide them. We don't want to be doing the quotient rule when we do that. Okay. So we'll go through a few of these. Typically people find this to be pretty nice, pretty simple and quick. So with this first one here, we're going to take our 0, we're going to plug it in. We would get 3 times 0 minus the sine of 0 all over 0. So obviously we get 0 here. Sine of 0 is a 0, so overall we get a 0 on top. You're going to get a 0 on the bottom. That's indeterminate. L'Hopital's rule can be used then for this. That's just us finding the limit now as x goes to 0 still, and we use the derivative. All right. So we take our derivatives, and now we go ahead and plug in. We would get 3 minus, let your x be the 0, cosine of 0 being 1. We get 3 minus 1 over 1. Our limit is 2. All right, and then that's our answer. If you have your calculator, you can throw that in the calculator real quick, graph it. You'll see as we get really close to the x value of 0, our y value is going to be 2. All right. All right, number 2. Same process. If I go ahead and plug that in, I would get root 1 minus 1. And then in my denominator, I get my 0. So we get a 0 on top, 0 on the bottom, indeterminate. So we use L'Hopital's rule. This has our half power, so we're going to take our derivative. 1/2 times 1 plus x to the negative half. The derivative of 1 would go away. And then my denominator's derivative is a 1. Clean this up. So there's our 1/2. In your denominator, you should have the square root of 1 plus x. Go ahead now, let your x approach 0. So as our x gets smaller and smaller and smaller and smaller to where it will ultimately become a 0, all we would end up with is a 1 on top, 2 times root 1 on the bottom, which is 2. All right, our limit should be 1/2. I'm sorry, this is messy. It's kind of hard to write small with this pen. All right, so our limit for that one is going to be 1/2. Go to our next one. Maybe if I do this, see if I can blow this up. Maybe not. 0 minus the sine of 0, and then 0 cubed. Zeros everywhere. So like you're going to find in this whole section, these are all going to be indeterminate, or otherwise I wouldn't have it in this section. We can go ahead and take our derivative. Oops. Easy. 1 minus cosine of 0, or cosine of x, and then over 3x squared. We would go ahead and plug that in. In this instance, we would get 1 minus cosine of 0 is a 1. In our denominator, if we let x be a 0, if we let x be a 0, you'll get a 0 in your denominator. So this is the first one where not only do you get a 0 over 0 with our initial function, but also when we take our first derivative, we get 0 over 0. As long as we continue to get 0 over 0, which we did, we can take the derivative again. So now in this one, you're going to get sine of x on top, 6x in your denominator. Let x be a 0. So, oh my gosh. So sine of 0 is 0. 6 times 0 is 0. If you notice now, the second derivative also gives us indeterminate form. Usually the eyes start to roll at this point, because now we have to do it again. Cosine of x on top, the derivative of 6x is in your denominator. Now, no chance we get a 0 in our denominator because we have that 6 here. So now we have to get our answer at this step. Next thing we do, take our 0, plug it in. Cosine of 0 is a 1, so you're going to get 1 on top. You're going to get 6 in your denominator. So our limit for this one should be 1/6. Okay, so that's pretty extreme in terms of having to go 3 times to be able to figure out what our limit is, but it's something that we are able to do. Okay. 4. Do 1 minus cosine of 0 is a 1, and then you would get 0 plus 0. So 0 is all around. Predictable. Take your derivative. We would get sine of x on top, 1 plus 2x on the bottom. Go ahead and let the x become a 0. Sine of 0 is 0. On the bottom, you would get 1 plus 0. So don't create something that isn't. This is not indeterminate. That means we have to be able to come up with our answer in here at this step. And we know 0 divided by 1 is 0, so that's our answer. 5 is a big one that you want to know. Initially, you're going to get your 0 over 0. Sine of 0, 0. 0 squared is a 0. So we do have that. When we take this derivative, you get cosine of x on top, 2x in your denominator. When we let your x be a 0, you'll get 1 on top over 0 in your denominator. When that happens after having used L'Hopital's rule, what this will tell us then, or what this does tell us, is this limit will be one of our limits that does not exist. We don't get 0 over 0 anymore, so we can't do L'Hopital's rule. All right, we get a 1 divided by our 0. If we were to graph this function, you'll see one of them is going to positive infinity from one direction. The other direction is going to be going negative infinity. Limit won't exist when that happens. Okay. 6. I want to make sure we see at least 1. This is not going to 0. All of these went to 0. So 0, 0, 0, 0. They don't have to have the x value going to 0. All right. It's just easier to get 0 over 0 when the x is approaching a 0, but that's not part of the rule. We can still use L'Hopital's rule. The important part is, do we get 0 over 0 when we evaluate our limit? And we will in this case. So if I took my pi over 2 and I do 2 times pi over 2 minus pi, and then in my denominator, the cosine of pi over 2, we would see that these 2's would cancel. You get pi minus pi in the numerator, and then we get the cosine of our 90-degree angle. That's going to be 0 over 0. This is the important part. The fact that it's indeterminate means we can use L'Hopital's rule even if our x wasn't approaching a 0. So that's not necessary. This is what's necessary if we want to use L'Hopital's rule. So in this case, we do get our 0 over 0. So we can go ahead and take our derivative, 2 over negative sine of x. We know we get 2 on top, so we should get our answer at this step. The y coordinate, the sine value at our 90-degree angle is a 1. It's a negative sign, so we get a -1, limit -2. All right. Typically, L'Hopital's rule is used for 0 over 0, but it'll also work for infinity over infinity. So if you think about, if my x is going to be getting larger and larger and larger, so we have 10, 100, 1,000, 10,000, 100,000, million, so on and so forth, and we square that, this number in the numerator is going to become big, 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 get larger and larger and larger. Yeah, it's negative. That's not terribly important, but that's going to be getting larger and larger and larger. And then definitely, if we are squaring it down here and multiplying by 5, the denominator is also going to grow unbounded, getting larger and larger and larger. So this is also indeterminate. This also tells us we can use L'Hopital's rule. So take our derivative. We would get 1 minus 4x top, 6x plus 5 in my denominator. We have the same issue. If I take 1 million, so my x just gets bigger and bigger, 4 times 1 million here. My numerator is continuing to get larger and larger and larger and larger. 6 times 1 million in my denominator, that is going to continue to get larger and larger and larger and larger. So this still gives us technically a negative infinity on top, infinity in my denominator. That's indeterminate. So like the one that we had done earlier, we can do this again. We would get -4 over 6 for our derivatives. That then gives us our answer. The limit of any constant is that constant. What's going on? So our limit should be -2/3. Hopefully some of you out there who are still awake are thinking, all right, do we really need to do L'Hopital's rule for that? Because we did have old rules for limits as x goes to infinity. So congratulations to you guys. We definitely want to use our old rules. Yeah, L'Hopital's rule will work for infinity over infinity, but remember what our old rules were for these. And for this one, as long as x was going to infinity, we would just look. If our degrees are the same, which they are right here, squared on top, square on the bottom, then our limit is really just their coefficient. And we would get the -2/3 right away. Same thing we got when we do L'Hopital's rule. Okay, so 8, you can do L'Hopital's rule if you want. We would get 3 on top and then 2x on the bottom. And then if you kind of think about what that would mean, I always get 3 on top. But as my x gets larger and larger, I'd be doing 3 divided by 20, 3 divided by 200, 2,000, 20,000, 200,000. And as we are dividing 3 by 200 million, so on and so forth, this number is going to be getting smaller and smaller and smaller. Same thing we would have gotten if we would have just used our shortcut rule, where here we have a degree of 1, here we have a degree of 2. The larger degree is in our denominator. When that was the case, our limit was always going to be a 0. Okay, now it kind of looks like a 6. All right, so that's L'Hopital's rule. All right, next up is this one. All right, on the next page, sorry, I had to take a picture of this because I couldn't find this for a hard copy. So let me move this up. Is the rate at which functions are going to grow. So come on up here, you. Okay. Anyway, if you look at the top, let me just hold it in place. These are what we just talked about, the rates at which functions grow. If the bigger degree is on top, these are our infinity rules, then our limit's going to be an infinity. If the bigger degree is in your denominator, our limit's going to be 0. And if we have the same degrees, your limits are going to be the coefficients of whatever those 2 terms are. All right, so old stuff, you're going to need to remember those. Going to pop up with all of these. Our little rule when we do these, if we have 2 functions, so if we kind of look down here and we have e to the x and we have x squared. Okay, so what this is just saying is, if I'm going to, again, look down at number 1, e to the x and x squared, and we want to know, all right, who grows faster? Like if they were in a race, which one of those would be growing faster? Whoa, do that. So our e to the x and then our x squared. What we can do is set up a fraction. So if you look back up here, take one of our functions, make it the numerator. Take one of our functions, make it your denominator. If our limit is infinity, then what that is telling us, if we kind of look back at the top of the page here, whenever, I can't move this one. Sorry, this is a picture. It's not working good. The reason we would get infinity, if you look at the top of the page where you get the infinity limit, x squared over x, the reason we get infinity is the faster growing function is on top. So we know that f would be growing faster than g if f is on top, g is on the bottom, and our limit is infinity. If we compare these functions and put f on the bottom, change this, and then put g on top, so f is on the bottom and g is on top. If our limit is 0, like it was here, the reason we're getting a 0 for our limit is the faster growing function is on the bottom. Okay? So if the faster growing function is on the top, f is growing faster. If it's on top, you're going to get infinity. If we get a 0, that means the function on the bottom is growing faster, and that's why you're going to get a 0 for your limit. Third option then is what happens if we get a constant. What that then means is, while one number might be bigger all the time, that's just telling us that they're growing at the exact same rate. So, not asking which is bigger, we're just asking which one is growing faster. Okay? So as we go to these, let me clear this out. And let's do some of these problems below. Maybe. All right, so if we have e to the x, x squared, and we want to determine who's growing faster, what we would do is set up a fraction, just like up here. So if I can write where we just set up our little limit here. Now it's blue for some reason, don't ask me why. But if we went ahead and compared these, take e to the x over x squared. Ugh, that's ugly. Compare them as we look for the limit as x goes to infinity. This is why we do Hopital's rule before this. These are both infinity over infinity. Like e to the x is going to get larger and larger and larger. X squared continues to get larger and larger and larger. It's of indeterminate form. So Hopital's rule, now that we've done that, we've done a few. If we apply that to this one and go ahead and take our derivative, so we'll get e to the x on top, 2x on the bottom. Go ahead and evaluate it. Same thing's going to happen. E to the x continues to get very big, and then 2 times a million, 2 times 2 million, 2 times 10 million is going to continue to get larger and larger and larger as well. Infinity over infinity. So again, indeterminate. Take our derivative again. E to the x over a2. Now what happens, we're going to get a 2 in our denominator all the time, but our numerator is continuing to get larger and larger and larger and larger. So this is 1 million divided by 2, 2 million divided by 2, 8 million divided by 2. What that would then be telling us is this number is going to continue to get larger and larger and larger overall, telling us that our limit is infinity. If our limit is infinity, it tells us that the function in the numerator is always growing faster. So in this case, e to the x grows faster than x squared. And that's really all we want to know. Which of these functions grows faster? Okay. All right, so e to the x would be x squared. We'll come back to number 2. Go to number 3. Next. Same thing. Let's take e to the x. You know what? Actually, let's flip this around. Let's put x plus 3 in the numerator, because it doesn't matter where we put them. And e to the x in our denominator, and find the limit as x goes to infinity. Both of these get larger and larger. All right, 1 million and 3, 2 million and 3, so on and so forth, and then certainly e to the x continues to get bigger. So our guy Hopital, We once again take our derivative. We get 1 on top, e to the x in our denominator. Now that we're not going to get indeterminate form, we have to come to a conclusion. If you think your numerator is always a 1, while your denominator is going to become huge very quickly. So you have 1 over a million, 1 over 2 million, 1 over 3 million, 1 over 100 million. What overall then is telling us this is going to approach 0 as our limit. Since this produces a limit of 0, it tells us the function in your denominator, this is the function in our denominator, is growing faster than the function in the numerator. Okay? So e to the x, once again, wins. All right, e to the x, next one, number 4, is squared off against x cubed minus 3x plus a 1. And then we're going to race e to the x. Find our limit as x goes to infinity. And like we said, these are both going to be going to infinity. X cubed is going to get larger and larger. Think about the graph of x cubed. X cubed, well, let me write over here with it. X cubed looks like this. So that's definitely going to infinity. And then e to the x goes to infinity. So they actually both grow very, very quickly. Okay, so both of them are going to infinity. So we can use Hopital's rule. Do 3x squared minus 3 over e to the x. Same idea. This parabola as we go to infinity, not worried over here, but as we go, x goes to infinity, grows forever and ever. E to the x is going to continue to grow to infinity. So another indeterminate form. So we take our derivative again. Get out of there. All right, not letting me erase that. We would get 6x over e to the x. Another one that goes up forever. E to the x is going to increase forever. So another Hopital's rule. We get 6 over e to the x. 6 over e to the x getting larger and larger and larger and larger and larger. This again is going to go to 0. If we go to 0, that means the function on the bottom is growing faster. Since we put e to the x on the bottom, he's the one who's growing faster. So we're finding right now e to the x, pretty good. All right, doesn't lose very often, our guy e to the x. So what I'm going to have you now do, so I'm going to create a little space, and I'm going to make a 4b. So if you have room in there, make a 4b problem. And we're going to take e to the x, since he wins a lot. He beat x squared up here. He beat a line here. He beat a cube graph here. Let's say they call in the heavy hitter, such as like x to the 100th. And they were going to race each other. Okay? So think about what that would mean. If we set e to the x on top, x to the 100th in our denominator, these both go forever to infinity. All right? They're going to increase forever. Well, think about what that would then require us to do. We'd have to take our derivative. That's easy here. E to the x, and then you would get 100 x to the 99th. But think about what's going to happen here, because that's going to get larger and larger. We'd have to crank through 100 derivatives before we come to a conclusion. All right, that would keep you busy for a while. But what would ultimately happen is that the numerator will always be an e to the x, and then eventually this guy here is going to turn into a constant in our denominator. So if this is still going to be an infinity in the numerator divided by a constant in our denominator, overall this ultimately has a limit of infinity. Limits of infinity, so if we go back up to here, tell us that whatever function is in the numerator is growing faster. So e to the x wins. All right, he still will beat x to the 100th. All right. Long term, we want to know some shortcuts here. So what we have just found, so maybe up here, let's put some general things down. E to the x is going to beat any old regular algebraic function. All right. But in terms of how do regular old algebraic functions grow, so it beat x to the 100th, we know that, but we would hopefully all agree that x to the 100th would grow faster than the x cubed that we dealt with. All right, down here in number 4, x cubed grows faster than an x squared. So that's our parabolas. And then x squared grows faster than a line, which is what we did here in number 3. Okay, so here's some things that will allow us to shorten this up a little bit. When we see these in the future, we do not want to have to do Hopital's rule for every single one of these problems. Okay, so e to the x will beat any of those functions, and then whichever one of these has the higher degree, so an x to the 100th beats x cubed beats x squared, and then x squared would beat an x to the 1st. All right, so that at least starts to shorten this up a little bit. But let's go back down. We have skipped a few, or we skipped 1, and then we've got to revisit 5, 6, and 7. All right, so now if we go to number 2, clear some space, we're going to take x squared, the natural log of x. Let's see what happens as we go to infinity. X squared looks like this. So as we, on the x-axis, go towards infinity, this is going to increase forever. Same with the natural log function. Natural log function looks like this. It does go up forever, even though it kind of does it slowly, which actually kind of answers our question. But it does go to infinity. So we do get infinity over infinity. So we can take their derivatives. 2x on top. 1 over x in our denominator. Oops. And then now this, let's clean this up a little bit. This would become 2x squared if we did a little bit of algebra there and simplify that fraction. Because now when that gets simplified, it's easy to see what our limit is. As x goes to infinity, the numerator continues to grow unbounded, getting larger and larger and larger. We're just dividing by a 1. So that would tell us that this limit is infinity. That tells us the function on top is growing the fastest. In this case, it is x squared. So x squared beats the natural log of x. The poor natural log of x doesn't really beat anybody. Okay, logarithms. You think about what exponential functions grow very, very quickly. Logarithms are the inverse of exponential functions. So if exponential functions grow very quickly, logarithms are going to grow very, very slowly. So our guy natural log of x, he tries very hard. All right, think about what that looks like. Starts out very good, but just no stamina. He does increase forever, but he does it very, 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 very slowly, if you can remember what that graph will look like. Okay? So then kind of the last thing to cover is what happens if we look at number 5, if e to the x squares off with 4 to the x, because now we have an exponential function versus an exponential function. So now e to the x races 4 to the x as we go to infinity. So these both grow unbounded. We're going to go ahead and do Hopital's rule. Derivative of e to the x, e to the x. The derivative of 4 to the x, I'm sure we all remember, is 4 to the x times natural log of 4. Well, these both still go to infinity, and what we would hopefully understand, we would get e to the x again for that derivative. Take the derivative of this guy, we would get another 4 to the x, and we would get another natural log of 4. So natural log of 4 squared. Can't squeeze that in there. Okay? So what you'll recognize is these will never go away. When we did 1 through 4, one of them, or at least 1, 3, and 4, and then the one that we had made up, 4b, one of them is going to turn into a constant. That's not going to happen in this type. So what we want to just get down and understand, when we compare an exponential function to an exponential function, what we are looking at is what is the base. So this is 2.7 to the x. This is 4 to the x. Hopefully intuitively we kind of just understand which one's going to be growing the fastest, and that's the one that's going to have the bigger base. So a 4 to the x is going to grow faster than a 2.7 base raised to the x power. So for this one, now e to the x meets his match, and 4 to the x will grow faster than him. So if we kind of started layering that, 10 to the x is going to grow faster than 4 to the x, so on and so forth. So if we start comparing things, all right, then we can go ahead and figure out, without L'Hopital's rule, which functions grow the fastest, okay? All right, and then quickly, these last couple, these just have the same degrees. Probably not the best one that I could have used for this, but since this is an x squared, and it's raised to a square root, this really does have a degree of 1. This has a degree of 1. So if we went ahead and set these up as a limit, you can verify all this on your calculator if you wanted. This has a coefficient of 1. This has a coefficient of 1. Our limit is a 1. What that tells us is these guys grow at the same rate. Okay? This one's always going to be bigger. Like this will always give you a bigger number, but their rate is linear. They're both growing at the same rate. Okay? And then last but not least, these guys, when we compare these, hopefully I can squeeze this in. Silly thing here. Move this up. No. All right. Get bigger. No. Log base 3 of x, and then the log base 5 of x as x goes to infinity. Whenever we deal with logs, we always want to rewrite these. That does not change. So we want to go ahead and rewrite this as the natural log of x over the natural log of 3. Oh gosh. Hope I can squeeze this in. Natural log of x over the natural log of 5. What then happens is these natural log of x's cancel. So if we went ahead and multiplied by the reciprocal of our denominator, what we should get, let me create a little space. Oops. What that should do is the ln of x's cancel, and I would get the natural log of 5 divided by the natural log of 3. If we went ahead and now did the limit of this as x goes to infinity, you're going to get that as your limit. And what we set up here is if we get a limit that's a constant, okay, or here, that's not a 0, not infinity, what that tells us is these functions grow at the same rate. So these two logarithms, since they're both logs growing very, very slowly, what we would say is these guys ultimately grow at the same rate. All right. All right. Well, that's pretty much all I have. I will attach, I'm glad I just thought of this, the calendar for this section so you would sort of understand what homework problems you would want to look at. If you wanted to try a few more of these, make sure you're all squared away with this. If you have any questions, reach out, let me know. What this section gets into is sequences and series, infinite sequences and series. So that's why we kind of want to know what our end behavior is. So that's why pretty much all of these, we're trying to figure out what happens as x goes to infinity, because that's what we're looking for in an infinite sequence. An infinite series is what happens as we go further and further and further to the right. So with that, one set of notes down, we really only got to know 6 topics in this chapter. So I'm going to see if I can just teach those 6 topics. Those are the things that are going to be on your AP test. So we're actually a little closer to the end of the year than what we normally would have been. But again, miss everybody. Hope to see everybody soon. If you have any questions, let me know. And I'll do my best to answer it. All right. We'll see you guys later, hopefully. Bye.